Hello, and welcome to my presentation covering machine learning random forest classification, focusing on impurity measures. My name is Burnett. Today we're going to cover decision trees and random forest and look at different types of classification functions or impurity measures. We're going to focus on Gini index impurity, entropy, misclassification error, and then we're going to wrap up with comparing them, looking at their advantages and disadvantages across the different classification functions and when we should use them. To give you a basic interpretable background, a decision tree is kind of like mirroring how humans make decisions every day. Decision trees and random forest are popular supervised machine learning algorithms. Decision trees are very easy to use and interpret because they do, in fact, mirror how we as humans make decisions. Here you can see an everyday life example. So as a human, you make decisions every day. For example, you will need to decide which food you're going to want to eat or even make to eat that day, which restaurant to go to, which clothes to buy every day, so on and so on. Now here, this picture shows how the decision tree is used for retailing that mirrors exactly what a human thinks and decides when buying a dress. Here is an example of a decision tree relating to our focus of machine learning. For example, if you want to predict whether a person cheats based on the attributes of refund, marital status, and taxable income, you can with this tree. The decision tree, in fact, helps us choose which attribute is, in fact, the most important. Then we make a prediction on whether or not that person will cheat or not. To help us better understand more about decision trees, here is a little bit of useful terminology for you. A root node, or parent node, it's the topmost part of the tree, which divides it into two homogeneous sets. The decision node is also referred to as the child node. It's a subnode which further splits it into two subnodes. The terminal, also called the leaf node, this is the lowermost node or nodes with no children that represent a class label. Basically, the decision taken after computing all the other attributes. Splitting refers to dividing a node into two or more nodes. The splitting technique results in fully grown trees until the criteria of a class attribute are met. But a fully grown tree is likely to overfit the data, which leads to poor accuracy on unseen observations. This is when pruning, our next term, comes into the picture. Pruning is the process of reducing the size of the tree by removing the nodes which play a minimal role in classifying an instance without reducing the predictive accuracy as measured by a cross-validation set. And finally, the branch is a subsection of a decision tree called the branch. The classification criteria. In order to make a good split at each decision node, we need classification criteria that gives us the maximum information gain. So you may ask yourself, what is information gain? Basically, using information gain, when we use it, we want to determine which attribute in the training data is most useful. So, in other words, it tells us how important a given attribute is. We will use it to decide the ordering of attributes in the nodes of a decision tree. Mathematically, the information gained is defined as the overall impurity measure, and then minus the proportional impurity measure of the left node and the proportional impurity measure of the right node. In the formula, I is the impurity measure, which can be entropy, Gini index, or classification error. One of those impurity measures. D sub P, D left, and D right are the data set of the parent left and right child node. We want to make a good split at each decision node, so we're going to have to use an appropriate classification measure. There are three types: Gini index, or also called Gini impurity, entropy, and misclassification error. Gini index, also referred to as Gini impurity, is an impurity measure method. It tells us how good the split is within the tree. The objective is to see whether the impurity is the lowest, so then we would stop splitting or continue to split. For an outcome variable with m classes, Gini impurity index is defined as 1 minus the summation of all the probabilities squared. The Gini index values lie in the range from 0 to m minus 1 over m for m class scenario. It lies in the range from 0 to a half for 2 class scenarios, where m equals 2. It is important to note that a higher value of Gini index implies a higher value of purity or homogeneity. Also, Gini index works well with categorical target or dependent variables. Now, the steps to calculate the Gini index impurity, there are 3. The first step is that we're going to calculate p squared plus q squared, where p and q are the probability of success and failure respectively. Step 2, we're going to calculate the weighted Gini index for each split. And step 3, we will compare the weighted Gini index value of each split. Then we will input the variable with a higher value that is chosen. So for example, suppose you want to group students based on whether they will play volleyball or not. And the population can be split using class and gender. Now the question is which one to choose to produce more homogeneous groups. The Gini index value will tell us which one to choose between class and gender. After calculating the Gini impurity, it tells us how mixed up or impure a set really is. The left picture shows a 0 impurity, as you can see, because we can differentiate all the apples to separate the basket successfully. The right picture shows 8/10 of impurity, indicating that the basket is mixed up. Our goal with classification is to split or partition our data into as pure or unmixed sets as possible. If not, we will have to split the tree even further. If we reach a 0 of Gini impurity value, we stop dividing the tree further. Just remember, the lower the impurity, the better. Let me walk you through an example that shows you how to calculate the Gini impurity. The first step is to compute Gini index on the left node, and then on the right node. The second step is to calculate the weighted average of the Gini index on both nodes. The good news is that we can follow the exact same steps at each iteration for building the tree. We then calculate all of the Gini impurity scores for the remaining variables. If the node itself has the lowest score, then there is no point in separating the patients anymore, and it becomes a leaf node. If separating the data results in an improvement, then we pick the separation with the lowest impurity values. Now that we've conquered Gini impurity, let's move on to the second type of impurity measure, called entropy. Entropy measures the randomness of the elements. Mathematically, entropy is defined as minus summation of different products of probability and logarithm of probability across m classes. The entropy values lie in the range from 0 to log squared of m for m class scenario, and 0 to 1 for a 2 class scenario. Entropy is 0 when the sample is completely homogeneous. The steps to calculate entropy are here for you. First, we will calculate the overall entropy of the target. Secondly, we will split the data set for different attributes and calculate the entropy for each branch. And finally, add them. Step 3, we find that gain equals entropy T minus entropy T of X. Step 4, we choose the attribute with the highest information gain. Here, I am showing an example that calculates entropy for a two-class variable. Let the probability of obtaining 1 and 2 and 3 on a dice be 0.5, 0.25, and 0.25 respectively. Using the math formula of calculating entropy in the previous slide with the logarithm in the function, the entropy here is 0.45 or 45 hundredths. Okay, we have learned two types of classification functions, Gini index and entropy. Our final one that I would like to introduce to you is misclassification error. This is the third type of impurity measure. Mathematically, misclassification error is defined as 1 minus the maximum of probability of success and probability of failure. The steps to calculate misclassification error are: 1. We calculate the overall misclassification error of the target. 2. We split the data set for different attributes and then calculate the misclassification for each branch. Third, we find the information gain for each attribute. And finally, step 4, we choose the attribute with the highest gain. This slide illustrates how to calculate misclassification error. Using the math formula of calculating misclassification error in the previous slide, the misclassification error is 0.5. All right, I hope by now you're starting to understand how to calculate the Gini index, entropy, and misclassification error a little bit easier, and you're becoming more familiarized with each method. Now, let's compare them for a two-class variable when m classes equals 2. As you can see in the graph, entropy hikes up much more sharply than Gini. This means it can penalize an impure node harder. Another difference we can see is that misclassification error is not smooth like the other two. Now, I know you're asking yourselves, what are the advantages and disadvantages of each impurity measure? Well, looking at the figure, the green square shapes are the entropy of the first two child nodes in the decision tree model above, connected by a green dashed line. The objective for the decision tree algorithm is to find the feature and splitting value that leads to a maximum decrease of the average child node impurities over the parent node. So if we have two entropy values left and right child node, the average will fall onto the straight connecting line seen here. Basically, the most important point that I want you to take away from this is that entropy is always larger than the average entropy due to its bell shape, which is why we can keep continuing to split the nodes in contrast to the classification error. An advantage of both Gini index and entropy is both are used to grow large trees as opposed to the misclassification error. However, entropy and Gini are more sensitive to changes in the node probabilities than the misclassification error rate. Some more advantages and disadvantages for us to focus on here are the entropy equation uses logarithms because of many advantageous properties. The main advantage is the additive property it provides. Nonetheless, entropy is more computationally heavy due to the log in the equation. Like Gini, the basic idea is to gauge the disorder of a grouping by the target variable. Instead of utilizing simple probabilities, this method takes the log base of 2 of the probabilities. Moving on, both Gini index and entropy are differentiable and hence more amenable to numerical optimization. All things considered, a slight preference might be for you to go with Gini, since it doesn't involve a more computationally intensive log to calculate. These are all important things to consider when choosing which impurity measure to use. Lastly, here are some useful practice tips when you should in fact choose Gini impurity and when you should choose entropy. Gini is intended for continuous attributes whereas entropy is intended for attributes that occur in classes. Gini will tend to find the largest class, while entropy tends to find groups of classes that make up around 50% of the data. Gini is a great way to minimize misclassification, and entropy is good for exploratory analysis. All in all, thank you so much for reviewing my presentation covering various classification functions of impurity measures. I hope that, in fact, this will help you in your future studies and endeavors to help make the world a better place.